Let's have a look at a problem on the buck converter. Let's say in a DC to DC buck converter, you have the input voltage of 100 volts. Then you have an inductance value of 0.5 millihenry. The duty cycle of the switch at which you are controlling is 50%. And it is also operated at a frequency of 10 kilohertz. Now, what is the average value of the output current if you look at that? So it is also given that the average value of output current is 2 amps here. And now, the values of the inductance and capacitance are already there in the picture. Now we need to basically find out what is the output voltage and the average value of the inductor current, then peak to peak ripple inductor current, and then we need to calculate the duration of turn on time and turn off time of the switch. And next, if we need to find of average inductor current is less than the delta I, means the ripple is much higher than twice that of the average current, then can we say that whatever we have calculated so far are correct? If not, then what are the modifications? How your output voltage is going to change and how inductor average current is going to change. And then if you don't want that corrections, but then if you still want to get the initial calculated values to be exactly same, not changed, then what modification do you suggest to the circuit? So that's what is point F here. So to solve this particular problem, this is a simple buck converter. In this buck converter, we have a 50% duty cycle. Input voltage is 100 volt. So assuming that your continuous conduction mode expressions are still valid, which we'll figure out later, you can say that, okay, my output voltage is D times of my source voltage. You're switching at 50% of duty cycle, that is 0.5. So 0.5 times of 100 volts is 50 volts for us. Output voltage is 50 now. The average value of the inductor current is going to be exactly same as the average value of the output current, because the average value of the current that is flowing through the IC average is equal to 0. So if you wanted to get the average value of the inductor current, then you can say that your value of IL average is exactly same as your I0 average, and that is 2 amps as what is given in the problem itself. And next, if you want to calculate the peak to peak current ripple, then the peak to peak current ripple in the case of buck converter, considering that the continuous conduction mode is still valid, it can be expressed as delta I is equal to V0 times of 1 minus D upon LF. Now you know that the output voltage is 50 and duty cycle is 0.5, that is 1 minus 0.5 for us, upon the value of inductance is already there, so that is 0.5 milli is 10 power minus 3, and frequency of switching is 10 kilo, so 10 times of 10 power 3 for us. So if you calculate what is the value of that current ripple, which will be 5 amps. Now, what we observe is the average value of the inductor current is much lower than the current ripple. That delta I is greater than 2 times of IL average. If delta I is greater than 2 times of average inductor current, this is indicating that your buck converter is operating a discontinuous conduction mode. So if your buck converter is operated in a discontinuous conduction mode, it is very clear that the output voltage will not be D times of Vs, but your average current will be exactly same as 2 amps. So what is the correction we need to make for the output voltage? We know that in this particular case, we say that the output voltage is going to be D times of Vs upon beta. Now, how do you get the value of beta? The value of beta is obtained using 0.5 times of beta times of Imax is equal to I naught average. This is what we had in the previous derivations. In order to get the correct value of output voltage, we need the value of beta, where the value of beta can be calculated using 0.5 times of beta multiplied by Imax is I naught average. Now, that 0.5 times of beta multiplied by the value of Imax is nothing but Vs minus V naught upon the value of inductance multiplied by beta t times, dt times is the value of Imax, which is equal to I naught average. We know that the I naught average is 2 amps for us. In this expression, the value of V naught can also be written as d upon beta times of Vs. So if you do that, then you know that this is beta by 2. Vs can be taken out. That will be 1 minus d upon beta dt upon the value of inductance is equal to 2. Now in this equation, we know the value of duty cycle is 0.5 for us. Time period is 1 upon 10 kilohertz. Value of inductance is 0.5 millihenry. Source voltage is 100 volts. So if you substitute all these numbers, then the only value that we don't know is beta. So then if you calculate what is the value of beta, you will get that beta value as 0.9. So once you have the value of beta as 0.9, then you can say that output voltage, that is V naught, is d upon beta multiplied by Vs, which is 0.5 times of 100. This value, if you calculate, it is going to be 55.56 volts. This is V naught. Now, we have seen that in the case of continuous conduction mode, we had output voltage for a duty cycle of 50% as 50 volt. But due to the discontinuous conduction mode, we have a duty cycle same, but the output voltage is 55.56. But the problem here is your current is going to be discontinuous. So if you want to know that what is the turn on time, like go back and see that there is a question on what is the respective duration of switch on time and off time. If you live with an assumption that the conduction mode is continuous, then for a duty cycle of 50%, you say that the half time you have switch conducting and another half time you have diode conducting. But this is a discontinuous conduction mode if you want to give a correct answer. Now you know that the half time the switch is conducting, but when your switch is turned off, diode is conducting only for the 0.9 times of D. Means it is from 0.5 times of T to 0.9 times of T because your beta is 0.9. So diode is conducting from the 0.5 times of T to 0.9 times of T. This is the duration in which your diode is conducting. You can say that it is 0.4 times of T is the time in which your diode is conducting. That is turn on. Now the next question is, if you say that, okay, you are in a discontinuous conduction mode, can we get the same output voltage as in A, means 50 volts, can we get same 50 volts by changing something in our design? So now why are we getting 55.56 or higher voltage than 55, or why our output voltage V naught is D times of Vs is not valid? So this is not valid because you have your delta I to be greater than 2 times of IL average. Or in a way, this is invalid because your value of inductance is less than the critical value of inductance. So this is what is pushing you into discontinuous conduction mode. Suppose if you could operate your circuit in a continuous conduction mode, then for a selected duty cycle of 50, you will be able to get 50 output voltage. Now, how can that be done? So one way is, let's say I have my inductance value less than the critical value, so can I increase it and make it equal to the critical value or higher than the critical value? Then for the 50% of duty cycle, you'll be able to get 50 volts that you wanted. So that is increasing the value of inductance is one way to go for it. The other way is, since your inductance is less, can you modify something else to bring down the critical value to be same or lower than the value of the inductance in my circuit itself? In order to do that, if you look at what is the expression for L critical, 1 minus D times of R upon 2F. This is an expression for the L critical, which means if you wanted to bring down that value of, one is increasing the value of inductance, if you want to bring down that L critical value to avoid the discontinuous conduction mode, then you can reduce it by increasing the switching frequency. Then L critical will increase. So another way is increasing switching frequency. You may say that I want to change R, but that will be changing the load itself. And if you want to change D, you are still going to be in a discontinuous conduction mode. Maybe you will be able to get 50 volts, but that is not a potential option that we have because we always prefer continuous conduction mode. So these are the two better options that you can look for in order to push your circuit from a discontinuous conduction mode to the continuous conduction mode, so that for the question you will be still able to get 50 volts as an output voltage for the duty cycle of 50%.